Previously, we had learned about what is a Heron's formula and its application in calculating the area of a triangle, correct? In this exercise, we are going to use the same concept to calculate the area of a quadrilateral, and that is our learning objective, right? Take a look at this example that is given to us. We have a quadrilateral ABCD with the dimensions as given, and we need to calculate its area, right? But the problem is that this is not one of those standard shapes such as either a square or a trapezium or a parallelogram. Had it been one of those cases, we could have easily applied the respective formula to calculate the area, right? But that is not the case here. Hence, we need to think of alternative approach, okay? And another good thing we have is that there is a side AB that is perpendicular to side BC, right? These two sides. Right, now what we can do is, if you think creatively, what we can do is we can divide this quadrilateral into two parts. Let's say if I connect these two vertices, I divide this into two parts by triangle 1 and triangle 2. If we can somehow calculate this dimension AC, then we can apply the Heron's formula with ease to calculate this total area, right? Because the total area will be area of triangle 1 and area of triangle 2, and we sum them up, right? This is going to be our approach, right? Now let's remember what is the Heron's formula for calculating the area of a triangle, right? In any triangle ABC, if it has respective dimensions as ABC of 3 sides, then we say that the area of such triangle will be equal to S times S minus A times S minus B times S minus C. And this whole thing comes under a square root, right? And we know that S is equal to the half of the perimeter of that respective triangle, right? This is what we have known, this is what we have learned, right? Now let's apply this method to these two shapes, okay? Now first we need to calculate AC, right? We can simply apply our Pythagorean principle because the dimension AB is perpendicular to BC, and we can say that AC square is equal to the square of the two perpendicular sides that make up that triangle, right? So that will be 9 square plus 40 square, right? And this would imply that the dimension AC, when you take the square root on both sides of this equal signs, then you obtain that equal to square root of 9 square plus 40 square, and that when you solve this mathematic you obtain that equal to 41, right? So this dimension is 41 in meters, right? All these dimensions are in meters, okay? Now let's take a look at our respective area of each triangle. So when I look at my triangle ABC, I obtain that first I need to calculate S1, right? So S1, which is just a terminology for finding the half of the perimeter of this triangle ABC, will be 41, which is this side, plus 40 plus 9 divided by 2. And when you solve this mathematic, you obtain that to be 45. And now when you apply this dimension into this formula, you obtain that the area of triangle ABC will be 45 times 45 minus 40, right? Then you will have 45 minus 41, and then you will have 45 minus 9, okay? And everything is under a square root, and I will let you, the students, calculate this mathematics, but we know that this result will be equal to 180 meters square because all of these dimensions are in meters. So we have one area, right? And likewise, let's calculate the area of the triangle ADC. In this case, I'm saying that the half of the perimeter is S2, right? Just to make it different from S1, is equal to 41 plus 17 plus 30 divided by 2, and that will be equal to the dimension 44, okay? So now let us apply this formula one more time. So we say that the area is equal to 44 times 44 minus 41, right? And then we have 44 minus 17, and then we have 44 minus 30, right? And everything is under a square root, right? This entire product of few numbers. And this is equal to the area. So when you calculate this mathematics, you obtain that this entire product after a square root will result in a value that will be equal to 223.4 meters square. And now you have the two respective areas. So let's say this is my area 2 and you have your area 1, right? So the total area will be equal to A1 plus A2, right? So that will be equal to 180 plus 223.4, and that comes out to be 403.4 meter square. Okay. So now you obtain your final result, right? But the main objective is not necessarily to highlight the computation or mathematics that we have here, products and square roots. The objective is to highlight that Heron's formula could be one good technique that you can apply in variety of situations. Whenever you see any irregular shapes and you can divide that shape into two or more parts, making some triangles, then you can obtain the area of that irregular shape by the summation of the individual areas. Okay, and that is the objective in this exercise, and that is where we say that how useful could be Heron's formula in calculating the area of complex shapes. Okay, with that we will take a pause here, and that concludes our discussion on the module of Heron's formula and its application.